Welcome back to another episode of CS50 Explained, where we break down complex computer science concepts into bite-sized pieces. This week we explored some foundational ideas that power how computers manage and manipulate data. Let's start with hexadecimal, a base 16 numbering system that helps us represent large numbers more compactly. In hexadecimal, we count from 0 to 9 and then use the first 6 letters of the alphabet, A to F. This means a single hexadecimal digit can represent values up to 15, where 10 becomes A, 11 becomes B, and so on until F or 15. For example, the hexadecimal number FF translates to 15 times 16 to the power of 1 plus 15 times 16 to the power of 0. We typically add 0x before hexadecimal numbers to avoid confusion with decimal numbers, like 0xFF. Now, let's transition to pointers, which are like signposts directing us to specific memory locations. Imagine you create an integer variable called n and set it to 50. That value gets stored somewhere in your computer's memory, and you can find its exact address using the ampersand operator. To store this address, we use a pointer variable declared as int star p. So if you write int star p equals ampersand n, p now holds the memory address of n, often displayed in hexadecimal format. When you use the star operator on p alone, this is called dereferencing. Dereferencing tells the computer to go to the address stored in p and retrieve the value there. For instance, printf %i \nkma star p would output 50. Pointers typically use 8 bytes of memory on modern systems to handle large address spaces. Also remember the special value null, which indicates a pointer isn't pointing to any valid memory location. You might recall using the CS50 library's getInt function early in the course. Under the hood, functions like getInt use scan, which takes 2 arguments, the format specifier and the address where to store the input. So scanf %i, ampersand number reads user input directly into the variable called number. Next, let's demystify strings by looking at their underlying structure. When you declare strings equals hi exclamation mark, s is actually a pointer to the first character in memory. Printing the addresses with %p reveals that s points to h, while s bracket 0 points to the same address as itself. C doesn't have a native string data type. The CS50 header provides this abstraction for simplicity. Traditionally, C developers use stars to represent a pointer to the first character of a string. Strings in C always end with a \0 character, which signals the end of the sequence. Consider what happens when you copy a string with t equals s and then modify it using to upper. Both s and t will show uppercase text because they point to the same memory location. To create a true copy, we must allocate new memory using malloc, like ** equals malloc strolens plus 1. After copying each character, applying to upper to t leaves s unchanged. Crucially, we must free any memory allocated with malloc using the free function to prevent memory leaks. Forgetting to free memory can lead to stack overflow, where your program runs out of available memory. This brings us to buffer overflow, a critical security issue. Buffer overflow occurs when a program reads or writes beyond the boundaries of allocated memory, corrupting adjacent data. A real-world example happened recently with a cybersecurity company whose system crashed due to an out-of-bounds memory read. Finally, let's discuss passing values versus references in functions. When you pass variables to a function like swap a b, you're actually passing copies of the values, not the original variables. This is called passing by value, so changes inside swap won't affect the original variables. To modify the originals, you must pass their addresses using ampersand and ampersand ya. Then inside the swap function, use pointer parameters and dereference them to swap the actual values. This technique is known as passing by reference. We applied these concepts in the recover problem set, restoring JPEG images from a forensic memory card. JPEG files have unique signatures, and we read the card in 512-byte blocks to find them. Each recovered image was saved with sequential names like 000.jpg. Handling edge cases taught us to manage file boundaries carefully, especially when JPEGs don't align perfectly with blocks. Understanding these principles unlocks deeper computer science insights and makes you a more effective programmer. Keep experimenting with these ideas, and join us next time for more CS50 explorations.